You've been there, right? Caught in a sudden downpour. But have you ever stopped to think about something as delicate as a butterfly in that same storm? It seems like there's just no way they could survive. But they do. So how? Well, we're going to dive into this incredible piece of natural engineering to find out.
I mean, seriously, just look at them. Their wings are so fragile, they're practically paper thin. And get this, a single raindrop can weigh 50 times more than the butterfly itself. That's just insane. So how on earth do they keep from getting totally waterlogged and just knocked right out of the sky?
Now, the answer, as researchers have discovered, isn't some kind of magical force field. Nope, it's something way, way cooler than that. The secret has been hiding in plain sight this whole time, engineered at a microscopic level right on the surface of their wings. All right, so to crack this case, scientists took a close look at 4 very different species of butterflies and moths. Each one has a totally unique wing design, which gives us the perfect set of clues to solve this mystery. First up on our list is the vibrant orange-barred sulfur. To you and me, it's this brilliant flash of orange, but if you zoom way, way in, you'll see its wings are covered in these super dense, overlapping scales. You can think of them like tiny little roof shingles, just perfectly designed to let water slide right off. Next, we've got the ghost-like glasswing butterfly, and its wings are almost completely see-through. So what's its secret? Well, it doesn't even have scales. Instead, its surface is covered in an array of tiny hair-like structures called microtrichia. Our third subject, the polyphemus moth, is playing a whole different ballgame. Forget those neat, tight shingles. Its wings are covered in these long, flexible, forked-shaped scales that actually look a little messy when you get up close.
And finally, the beautiful Luna moth. Its design is a hybrid, a mashup. It has both those fork-shaped scales we just saw and the tiny hair-like microtrichia. It's kind of like a microscopic shag carpet, combining 2 different strategies into one. So there you go, 4 species, 4 totally different game plans.
So how in the world do you scientifically compare these different surfaces? You need a way to measure just how complex and textured they are. And that brings us to a really key concept. It's something called the roughness factor. Think of it this way. Imagine a flat piece of paper. Its roughness factor is really low. Now, crumple that paper up into a ball. You've got a much larger surface area packed into the same small space. That's a high roughness factor. So the bottom line is this. A wing with more bumps, ridges, and complex structures is going to have a higher roughness factor. And this measurement is going to be key to figuring out which design is the most effective at repelling water. Okay, so we've got our subjects and we've got our key measurement. It was time to put these wings to the test. Scientists basically just placed water droplets on each wing to see how they'd behave. The measurement they were looking for is called the contact angle. A low angle means the water spreads out and wets the surface. Not good. A high angle, anything over 90 degrees, means the droplet beads up into a tight little ball and sits on top, ready to roll off. The higher the angle, the more water repellent, or hydrophobic, that surface is. First to the plate, the orange-barred sulfur with its roof shingle scales. And the score is a very impressive 115.5 degrees. That droplet is just beaded up perfectly, barely even touching the wing. Okay, now for the glass wing with its invisible hairs. And would you look at that? It scored exactly the same, 115.5 degrees. This is fascinating. It shows that 2 completely different microscopic designs can get you the same high level of water repellency. Next up, the polyphemus moth with those long forked scales. And here's our first real surprise. Its contact angle is only 94.8 degrees. Now, that's technically hydrophobic, but it is much lower than the others. You can see the droplet is sitting a lot flatter. What's going on here? And for our final contestant, the Luna moth with its hybrid shag carpet design. And folks, we have a winner, a whopping 120.3 degrees. That's the highest contact angle of all. The water bead is sitting up like a perfect little sphere, which means it has extreme hydrophobicity. Okay, so we've got our results. The Luna moth is the undisputed champion of water repellency, but the real mystery here is the polyphemus moth. It has a super complex surface, so why did it perform so poorly? It's time to connect the dots. This chart really tells the whole story. The Luna moth, with its combo of scales and hairs, had the highest roughness and the highest water repellency. That makes sense. But then you look at the polyphemus moth. It has a very high roughness factor, even higher than the orange-barred sulfur.
but it had the lowest water repellency. Something just isn't adding up. And here's the solution. The problem isn't the roughness, it's the structure itself. You see, those long forked scales on the Polyphemus moth, they're just too flexible. When a water droplet lands, its weight actually causes the scales to bend. This lets the water sink in and make more contact, which totally tanks the contact angle. So the lesson is, it's not just about being rough, it's about being rigidly rough. But a water droplet sitting still is one thing. What happens when rain is actually falling? Well, the researchers ran another test, this time dropping water onto the wings to see how well they could bounce it off.
And get ready for this, because this is the biggest twist of all. The Polyphemus moth, the one that was the least water repellent, was the bounciest. Its flexible scales, which were a disadvantage for a still drop, acted like tiny trampolines, actively launching the falling droplets away. This just proves there's more than one way to stay dry in a storm.
So, what's the big takeaway from all this? Why spend so much time looking at butterfly wings under a microscope? Well, because these tiny structures hold the key to some incredible new technologies.
This whole field is called biomimicry, learning from and mimicking nature's best ideas. By understanding these different wing designs, we can create better self-cleaning windows, advanced water-repellent coatings for your jacket or your phone, and even surfaces that prevent ice from forming on airplanes. The possibilities are huge. And this really brings us to the final thought. The solutions to some of our most complex engineering challenges might not be waiting for us in a lab. They might be fluttering right outside our window. It just makes you wonder, right? What other amazing secrets are out there, hiding in plain sight, just waiting for us to look a little closer?